Well, so what's sort of our last idea? And it connects back to what we talked about last time. So we were talking about, we have our differential equations, and we were talking about, in particular, this notion of radius of convergence. And when is our solution valid? Which is a nice thing to know. It's nice to say, okay, I have a solution, but of course the follow-up question is it valid? Well, that's actually an important question. And so that's what radius of convergence gets to. It says, yes, my solution is valid, and it applies in this range. So we say, okay, well, how do you find it? There's this really painful process of, if you can figure out an explicit way to write the coefficients, and you look at the ratio of the coefficients, and you take that limit, or maybe if you're like, oh, I could maybe, pull out my really snazzy Calc 2, Math 166, and say, do a root test or something. But this can be a little bit hard sometimes. So we'll put quotes in hard. So it'd be nice to have something which was easier and say, we can say for sure we work with up to this extent. And so that's what today is to say, all right, what can we say? So we're going to talk about an ordinary point. And that's just to say an ordinary point is a place where your differential equation has nice pieces. So we're going to look in particular at a second order differential equation, because that's about as far as we feel comfortable with our tools. Y double prime plus p of x y prime plus q of x y equals 0. And then we say it's this ordinary point if the pieces here, the p of x and q of x, there's this technical word, analytic. Now, analytic basically just says nice. Nothing's blowing up. No big surprises. No huge infinite asymptotes or anything. So that's what we mean. It's a nice function. It's one that you could turn into a power series if you wanted to. You say, all right, well, great. Well, what if it's not nice? Well, then singular. And when something's singular, well, it usually means, things can go wrong. Be careful. Tread softly, because, things may not work out quite as much as you like. All right, well, how does this relate to radius of convergence? Well, we have the following. If x equals a is an ordinary point, then there are two linearly independent series solutions which converge near x equals a. Okay, that's the second sentence here. The radius of convergence is at least as large as the distance to the nearest singular point. All right. So what does that tell us? Well, here it says, hey, it says don't go through that process we were talking about last time. We say, look, this can help us tell us where our solution is valid. And so what we can do is say, instead of having to go through and do some complicated, what do the coefficients look like, we can instead say, well, where are the singular points? So help us show our solution is valid. Now, if of course you like reading the footnotes, you'll notice that there is an asterisk here. It says singular points can be complex. And when we talk about complex, we don't mean just complicated. We actually mean complex as in complex numbers. All right, there is another thing I want to talk to. I want to go back to this first sentence. So it says, look, suppose you have a nice differential equation in this form, then you have two linearly independent series solutions which converge near x equals a. Now, normally when it talks about our two solutions, what that refers to is the following. We say, all right, we have this differential equation, y double prime plus p of x y prime plus q of x y equals 0, and we make two sets of assumptions. Namely, we say, well, look at the initial conditions, y of 0 equals 1, y prime of 0 equals 0, And then the other one, you sort of flip. Y of 0 equals 0, y prime of 0 equals 1. And these are linearly independent. And the reason that is you say, look, whatever the solutions turn out to be as far as the power series, one of them can't be a multiple of the other. Well, why not? Well, look, if I start with this series, I can't scale this series and then up here because my constant is 0. There's no way you can scale 0 and get 1. Now, on the other hand, if I start with this series, I say, well, look, my coefficient of x is 0. There's no way to scale that and make the coefficient of x be 1. So they aren't multiples of each other, and for two functions, that's what it means to be linearly independent. So if you ever see a problem asking, give two linearly independent solutions, they're basically saying, look, just make very simple assumptions about our initial conditions. All right. Well, that's the idea. What about the practice? Okay. So here's a question. Determine whether 0 is an ordinary point for the following ODEs. All right, so our goal is 0 an ordinary point? All right, so we have three differential equations. Okay, all right, I like our odds. We can figure one of these out. Let's start with the first one. Okay, is 0 an ordinary point of this differential equation? What do we look for?
Two functions are
well, first we should write it in the form. That's our testing form. Okay, so we'll start here. Y double prime, because I'm going to divide through, plus sine of x over x, y prime, plus x, y equals 0. All right, now we're interested in these pieces. And the question is, are they, the phrase was analytic, but let's just say, are they nice? Well, we'll start with perhaps the x first. Is x a nice function? Can it be written as a series? Yeah, it is. It's right there, x. That's the series for x. What about sine x over x? Is that a nice function? Yeah, it is nice, right? Because what do we know about sine of x? Well, we know a lot of stuff. We're like, oh, Steve's going to go on his rant. Sine is strange. Sine is weird. Sine is unusual. Sine is odd. No, but that's not the rant. The rant is that we actually know sine of x has this power series attached to it. So negative 1 to the k, x to the 2k plus 1 over 2k plus 1 factorial. You don't need to know this, but when I say you don't need to know this, you don't need to memorize this. Of course, it's nice to know such a thing exists. So what about sine x over x? What happens to that? Does that have a nice series? Yeah, we divide by x. And it's the sum, k equals 0 to infinity, of negative 1 to the k, x to the 2k, over 2k plus 1 factorial. So this is analytic, and that is analytic, so that's great. So, is 0 an ordinary point? Yes. Okay, now let's push this even further into our fact. Say, okay, so we know nearby it has solutions. How far will our solutions extend? All right, so we start looking at this and saying, okay, when I want to know how far my solutions extend, the real question is, how far are these pieces, these series, are they valid for? How far can I go? What? Infinity. Yes. These functions are great everywhere. So our solutions are valid for all x. So even without actually finding our solutions, we know that they'll converge everywhere, which is wonderful because there's no singular points. All right. Cool. Cool. Okay. One down. Let's look at our next candidate.
I have a question about the last one.
Oh, there's a question about the last one. Yes.
Is the reason that sine of x over x doesn't blow up because we can write it as a series? Because normally it would be not valid at 0, right?
Well, yeah, so the question is sine x over x. What do you do about 0? So technically speaking, sine x over x, when we look at it, has a hole at 0. It's not defined at 0. But away from 0 is perfectly fine. But of course you can say, well, can we patch the hole? In other words, if you take the limit as x goes to 0 of sine x over x, do you get a value? And the answer is it turns out to be 1. And so when we think about sine x over x, we really think of, so technically sine x over x looks like this, where you have a sine curve, but it sort of fades as you move away. And say, okay, so what we do is we come in and we boop, patch the hole. So we'll think of sine x over x as representing this function here. All right, our next candidate, y double prime plus, whoops, I can write plus xy prime plus square root of x, y equals 0. Is 0 an ordinary point? Okay, I see a lot of yeses and some head nodding. Would anyone like to take an opposing view? No, you don't want to take an opposing view? Or the answer is no. Okay, let's look at our pieces. Is x a perfectly good function? Yes, no problems. What about square root of x at x equals 0? What happens with that function? And Steve starts drawing it as though something is going to happen. It looks like that, yes? Well, there's a couple of issues. One, it's not defined for negative x. What's the first derivative of square root of x at x equals 0? 1/2 x negative 1/2. So at 0, that becomes undefined. It has that vertical asymptote. Is this analytic? No. See, the problem is that this, it blows up in the first derivative, so it's not an analytic function. So it looks relatively benign, especially compared to sine x over x, but it turns out that 0 is not an ordinary point for this case, because the square root of x has issues. All right. Okay, 2 down. Do we have a question on this one we just talked about? Okay, well, we'll put some space here. Now we have our last one. So we have x squared plus 2x plus 2 y double prime plus xy prime plus x squared y equals 0. All right. Well, what would we do here? Yeah. We get into the right kind of form, right? We want y double prime plus p of xy prime q of xy. So y double prime plus x over x squared plus 2x plus 2 y prime plus x squared over x squared plus 2x plus 2 y equals 0. Okay, so looking at these functions, and just remember, we only need to care about 0 right now. Near 0. Are these nice functions? Someone is like, yes. Nodding their head. I'm feeling it. I'm feeling good about these functions. And these are nice functions. So yeah, these are good. These are good. Okay. And so when we have polynomials or polynomials, those are actually nice functions, and they are analytic as long as, what do we need to avoid? Zeros in the denominators. As long as you avoid zeros in the denominators, these functions are wonderful functions. Okay, so these are nice. Okay, so in particular, 0 is an ordinary point. Well, now we can then transition to talking about, well, what's our radius of convergence? We didn't talk about radius of convergence in the previous one because it's not an ordinary point, so forget it, hopeless. You know, the question is, you know, what's our radius of convergence? We're guaranteed. Well, the question is, how far is the nearest singular point? And it's like, well, you're already there. So that just says, if there is a solution, we're guaranteed it works in a radius of 0, which is not very useful. All right, 0 is an ordinary point. So let's talk about this. So where is our nearest singular point? If you like, where is the nearest point where things blow up? When the denominator equals 0. Okay, so when does x squared plus 2x plus 2 equal 0? Stops with I. Okay, well, how could we figure that out? Oh, I've got a converted person. Complete the square. All right. Well, our quadratic formula, they both work great. All right. Well, we'll do quadratic formula since that's on the sheet, right? Negative b plus minus square root b squared minus 4ac all over 2a, which becomes negative 1, negative 2 over 2, plus or minus, what comes out? So it'll be 2i, because it's square root of negative 4, 2i, divide by 2 becomes I. Okay, so what does that say? Well, think about, we're living in what we'd call the complex plane. So we'll call this C for the complex plane. Now, if you've never met the complex plane before, the idea is you have an axis which represents the real part and an axis which represents the imaginary part. We're interested in what happens at 0, which is the origin. And we come over here and we say, well, we blow up at negative 1 plus I, and we blow up at negative 1 minus I. So I move over negative 1 in the reals, up 1 in the imaginary, or down 1 in the imaginary. So if I want to know where my solution is guaranteed to be valid, it's this distance here. So it's guaranteed to be valid up until you hit your first singular point. That's what our fact says. So it's going to be around 0 is fine, but of course, you know, how much around 0? So what do we need to figure out? Yeah, it's like figuring out the radius of the circle. So it's asking, like, how far is that from 0 out to negative 1 plus I? So can anyone help us figure this out? Square root of 2. Because you can think of this like I moved over 1, I moved up 1. So there's like a right triangle 1, 1. You can even think of this as like a pair of coordinates, negative 1, comma 1. So this has radius square root of 2. And so in particular, the punchline here is we're guaranteed solution converges within a radius of square root of 2. Now, after square root of 2, might it converge? Well, maybe. We can't rule that out right away. But what this is saying, you're absolutely guaranteed that within square root 2, things are going to work out. And in general, you can say the following. If you have a of x, y double prime plus b of x, y prime plus c of x, y equals 0, where a of x and b of x and c of x are, whoops, got to be careful here, all polynomial, then what you look for, the key is find the zeros of the leading coefficient. Those will be your singular points. And that'll tell you how valid you are. Okay. All right. Cool. Any questions? All right. Well, the rest of today is mostly just practice. I have a bunch of problems written out. Is it all right if we jump around? Let's do this one. Mostly because, not that it relates to what we're talking about, but just because I want people to have practice with this kind of a problem. So given that y is the sum k equals 0 to infinity of ck x to the k is a solution to the differential equation y double prime plus y squared equals e to the 4x, with y of 0 equals y prime of 0 equals 0, find C0, C1, C2, C3, C4. All right. Do we have the technology to do this? Yes, we do. Okay, we can do this. We can figure this out. Now, you might say, well, can't we just plug something like this into Wolfram Alpha and it'll tell us the answer? So I'll tell you. I went into Wolfram Alpha today and I typed in this differential equation. And Wolfram Alpha said, this is a differential equation. And I can't tell you anything else. It doesn't know the explicit solution. They might say, that doesn't seem like a very hard equation to write down. That is correct. It turns out we struggle to solve differential equations. The ones that we focus on are the ones that we've made progress on. And there's a lot that we don't make progress on. Okay, so how do we approach this problem? Well, what should we do? All right, we'll take derivatives of y, and ultimately what are we going to do as sort of like our generic first step? What's our idea? Plug in. Yeah, that's our generic first step. We plug in. All right, so we're going to need y double prime. We'll make some notes here. Y sum k equals 0 to infinity, ck x to the k, y prime sum k equals 0 to infinity of k ck x to the k minus 1, y double prime sum k equals 0 to infinity k times k minus 1 ck x to the k minus 2. All right, so we plug in. We have y double prime sum k equals 0 to infinity k times k minus 1 ck x to the k minus 2. Okay, there's our y double prime. Plus y squared. All right, so that's plus the sum k equals 0 to infinity of ck x to the k squared. And that's going to be equal to e to the 4x. Well, can we do anything with e to the 4x? We can write it as a sum. How do we do it? Like if we were on a test or a quiz, what would we do? Yeah, we'd grab the formula sheet because this is one of the things where we have series for. It's a known series. So this is the sum k equals 0 to infinity of 4x to the k, which we can really write as 4 to the k, x to the k over k factorial. Okay, so here are our pieces. Now, among these pieces, which one do we look at and be like, That one, okay, all right. That one is like, we are not in our happy place. Okay, so, what can we do? Well, what we can do is say, well, what we have is really, we have this sum, C0, C1x, C2x squared, plus dot, 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 times C0 plus C1x plus C2x squared, plus dot, dot, dot. That's y squared. So what can we do here? It is just a polynomial. Oh my gosh. Oh, Steve, you made it too easy for people. Oh, that's okay. Should we make it more interesting? What? Yeah. We're changing this to a 1. Okay, good. Now we've made it more possible. We like possible. Possible is good. You'll see why we're changing it to a 1 makes it more interesting. All right. So what can we do here? Good. We meditate. We think about these things. That's a great approach. Do we have ways to multiply series together? Yes, it's called foiling. So it's multiplying polynomials together. So for example, what's the constant term going to be? C0 times C0. Plus, what's the next term going to be? Well, you have to take a constant times x, or the x term times the constant term. So in one case, you'll get C0, C1x. The other case, you'll get C1x, C0. When we put those together, what do we end up with? 2C0, C1x. Plus, what's the next term going to be? Well, we'll have a C0, C2, x squared. C1x becomes C1 squared x squared. C2x squared C0 becomes C2 C0 x squared. So if we put those together, we'll get 2C0 C2 plus C1 squared x squared. And then dot, dot, dot. Okay, now at some point you might be saying, why are we doing this to ourselves, Steve? But let's suppose we've gone past that and be like, we're embracing the challenge. There's actually a different question that I think you might want to ask. Why are you stopping at x squared? Because that seems like a choice that's being made. And there is a choice being made there. So why that choice? Not radius of convergence, yeah. So there's something, there's sort of like a kind of, I don't want to say hidden, but maybe it's a more subtle thing that we haven't been very explicit about. So let's talk about how many things are we looking for? We're ultimately looking for 5, yes? Are any of these freebies? Yeah. So these C0, C1, these are going to come from our initial conditions. Okay, so those we don't have to work for. So we changed that so that they were both 1s. Right now, if they were both 0, what would happen to this expression? It'd be 0. And I'd be like, oh, that's sad. For reasons which you'll see in a second. Okay, so that means how many more do we have to find after we've used up our freebies? We have 3 left to find. Now here's the idea. This is how all these work. Whenever I'm looking for coefficients, every term, and I'll explain what I mean by term, gives me 1 more coefficient. So when I say every term, I look at the constant coefficients of this expression. I group all the constant coefficients. That'll give me 1. Then I group all the coefficients of x, that'll give me my next one. Then I group all the coefficients of x squared, that'll give me my next one. So every time you look at your next coefficient, grouping all the coefficients together, of course, that gives you one more constant. So we need 3 more constants. So that says we need to compare the coefficient of 1, the coefficient of x, and the coefficient of x squared. And therefore, we really don't need the coefficient of x cubed. If we had asked for C5, then we'd need it. But we didn't. So we don't. Does that kind of make sense? Okay. All right. We'll let you meditate it on during the break. You'll be home, sitting around having the turkey. The whatever is in turkey that makes people tired will kick in. And then you can be like, oh, that's why. It'll all make sense. Okay. So, all right. So now let's talk about some other pieces here. So this sum, since we're not going to write this as a nice closed form, let's actually just talk about the first couple of terms. What's the first term going to be that actually still hangs around? So, yeah, it'll start at k equals 2, and the value will be 2 times 1 times C2. So it's going to be the first term is 2C2. What's the next term that's going to hang around? Yeah, so 3 times 2, which is 6, C3x. What's the next term that's going to hang around? 12, 4 times 3, C4x squared, plus dot, dot, dot. Yes? Okay. Well, let's come back over here. What's the first term look like? 1. How about that next term? 4x. How about the one after that? 8x squared. Because it'll be 4 squared is 16. 2 factorial is 2. 16 over 2 is 8. Plus dot, dot, dot. Okay, so here's how we can rewrite our problem. We have 2c2 plus 6c3x plus 12c4x squared plus dot, dot, dot plus c0 squared plus 2c0c1x plus 2c0c2 plus c1 squared x squared plus dot, dot, dot is equal to 1 plus 4x plus 8x squared plus dot, dot, dot. Now, we can always do this, by the way, for any series problems that we have. What's our next thing to do? Group. Okay, so we can make some notes here. So we'll have our constant, coefficient, our x coefficient, and our x squared coefficient. So we can just sort of group on the side. What's our constant coefficients going to be? C2, C0 squared, and that needs to equal 1. Do you see what's going on here? We grab our constant coefficient, grab our constant coefficient, grab our constant coefficient. How about our x coefficient? What will we have? 6c3. 2c0c1 equals Okay, our x squared coefficient, 12c4 plus 2c0c2 plus c1 squared equals 8. Now, we're most of the way done. Let's talk answers. What is C0? 1. And we know it's 1 because of initial conditions. What's C1? 1. Initial conditions. What's C2? Okay. Come to the constant coefficient. After you get past the initial conditions, you just work from the starting coefficients and work your way up. So the constant coefficient, we know C0 is 1. So 2c2 plus c0 squared, which is 1 squared, 2c2 plus 1 equals 1. So c2 is 0. How about c3? 6c3, okay, go to the next coefficient, 6c3. 2c0c1, well, 2 times 1 times 1 equals 4. So we get 6c3 plus 2 equals 4. So subtract 2, divide by 6. C3 equals 1/3. Okay, last one. We have 12c4, 2c0c2, c1 squared equals 8. Well, what's c0? 1. What's c2? 0. c1 squared? 1. So you get 12c4 plus 1 equals 8. So what is c4? 7/12. Okay, and now what do we do? Yeah, we're done. That's it. All right, so we can handle things which, what makes this one hard is this is not linear. This is not a linear differential equation because of that y squared. But we can still apply the same idea. We can still plug in y as a series. We can do this expansion. And if you go back in your notes, you'll see it was also called convolution when you multiply things together. And you still look at your coefficients and you group and nice things happen. And so there's this nice philosophy which helps you say, how far do I have to go? So initial conditions will give you the first few, and then however many ones you have left, that's how far you have to look.
Can you find the equation for the e to the 4x?
Uh-huh.
If you plug in k equals 0, don't you get over equation over 0?
Well, what is 0 factorial? So 0 factorial is 1. All right. Why is 0 factorial 1? It's not on the formula sheet. Now, if you're a computer scientist, you say, well, yes, because the way you read this equation is 0 does not equal 1, and that's a true statement. So yes, it is true that 0 factorial equals 1. But, you know, we're not all computer scientists. How do you think of factorial? Yeah, you like multiply, right? So factorials we think of as multiplication. So like 5 factorial, we multiply 5, 4, 3, 2, 1. We multiply 5 things. 4 factorial, we multiply 4 things. Okay, keep that in mind. We're going to switch and ask a different question. Suppose I'm adding things up. If I add, say, the 5 numbers 1, 2, 3, 4, 5, then you say 15. You'd think about it for a second, but yeah, 15. If I add 3 numbers, 1 plus 2 plus 3, 6. What if I said I have no numbers to add? What do I have? 0. I think most people agree on that. Like, yeah, if you don't have anything to add, you have 0. Why 0? What's special about the number 0? Yeah, well, so like if you add 0 to something, you don't change it. So there's a special term for this. So 0 is called the additive identity. So in other words, it's a number where if you do nothing, if you add it to another number, it does nothing. And so it's sort of like a base number to start with. So if you start with nothing, we say we start with 0 as far as addition is concerned. But that's addition. Switch gears to multiplication. Okay, so now we're not adding, we're multiplying. What's a number that when we multiply does nothing? 1. That's the multiplicative identity. So if I multiply 5 numbers, like 5 factorial, well, that would be 120. If I multiplied 3 numbers, 3 factorial, 3 times 2 times 1, that would be 6. If I multiplied no numbers, which is 0 factorial, what should I have? 1. So if you've multiplied nothing, you have 1. So that's the convention. Now that's sort of a mathematical response. Probably the more honest response is, well, it just makes the equations nicer if we assume that. So that's why we do it. Okay. Well, let's talk about this example for a few minutes. We probably won't go all the way through this. So this is a problem which came from a practice problem from a year ago. It showed up again as a practice problem in the spring. It wasn't on an exam, I'm glad to announce. It says find the recurrence relation for the coefficients of the series solutions around x equals 0. By the way, if you see things like recurrence relation, what does that mean? That's when you gather the coefficients into a single sum, what's the coefficient of x to the L? Now, not everything needs a recurrence relationship. So the previous problem, for instance, we didn't find a recurrence relationship because, well, we didn't need to. It was just easier just to group coefficients, which is perfectly fine. So, okay, we'll skip that for a moment here. We want the series solution around x equals 0 for the following equation. And get the first few terms, C0 and C1, as 2 constants. So C0 and C1 are meant to be arbitrary values here. And so if you're looking for your linearly independent solutions, one way to do it is just say, look, your constant is arbitrary, your coefficient of x is arbitrary. And the differential equation is xy double prime minus y prime plus y equals 0. Now, given what we've talked about today, not the one we just talked about, but from earlier today, do you see any potential issues with this question? What do you see here? Yeah, because I've highlighted it. Yeah, good. What does that say? Because we're going around x equals 0. How near is our nearest singular point? We're at a singular point. So this is like, whoa, danger, Will Robinson, danger. So x equals 0 is a singular point. Now what does that mean? Well, it means things may go bad. It doesn't have to go bad, but it could go bad. Well, should we see if anything goes bad here? Let's just delve into it. Just tip our toes into this. So we would start, we say, look, y is our solution. So 0 to infinity, ck x to the k, y prime, sum k equals 0 to infinity, k ck x to the k minus 1, y double prime, sum k equals 0 to infinity of k times k minus 1, ck x to the k minus 2. Now, in the interest of time, I just want to emphasize something weird is about to happen. So I'm just going to look at a couple of our coefficients here. Okay, so if I write down the first few terms of this series, well, this is c0 plus c1x plus c2x squared plus c3x cubed. Here, what would we have? Does anybody see what we'd have? We have 0, c1. A spoiler, you just take the derivative of what's above. 2c2x, 3c3x squared, dot, dot, dot. Okay, how about y double prime? 0, 2c2, 6c3x plus dot, dot, dot. Okay. So I'm just going to do a few terms just to emphasize what's happening here, because in the interest of time. All right, so we have x, y double prime, 2c2 plus 6c3x minus y prime, c1 plus 2c2x plus 3c3x squared plus ry, c0, c1x, c2x squared, and I'll stop at that point, equals 0. All right, well, what would we do next? Group coefficients. Okay, so the coefficient of 1. And remember, you have an x, which is going to multiply in here. What's the coefficient of 1? Minus c1 plus c0, and that has to equal 0. Well, wait a second. What does that say about c0 and c1? They have to be equal. That says they're not arbitrary. You can't pick one and then pick the other. You have to pick them the same. What? That's weird. Okay, how about the coefficient of x? Okay, we get 2c2 minus 2c2 plus c1 equals 0. What does that tell us? c1 equals 0. What? Not only are they not arbitrary, they're both 0. This is not looking good for us. C0 and C1 both have to be 0. So this is, this is why danger, weird things happen. If we assumed that, C0 was 1 and C1 is 0, it would break down. The series solution wouldn't work. Okay, well, what about x squared? What would that say? 6c3 minus 3c3 plus c2 equals 0. And from here, you'd say, C3, you solve for larger ones in terms of smaller ones, well, is minus 1/3 C2. And the process continues. Now, what happens here? Well, what happens is it turns out you're forced to choose C0 and C1 to be 0. They're not arbitrary constants. They have to be 0. And then C2 is a free choice. Everything else after that can be written in terms of C2. I haven't justified that with the work here, but it can be done. And you might say, well, where is the radius of convergence of the rest of the series? And I'll tell you, it turns out it converges everywhere. But, it's weird. Danger. But we won't give you anything like that. All right, well, thank you for being patient, and that's the end of today.